Hey guys, I'm going to go ahead and kind of cover the three key terms involved in circuits that you really need to know. It'll also help you with your drawings and understanding your drawings. Okay? Um, Make sure you've read the summary or the guided notes that I've provided for you. They're extremely helpful. So we are going to cover current, voltage, and resistance. Okay? Let's do that first, and then we can move to the actual simulation. I can kind of give you guys a little bit of guidance on the simulation and how to draw your circuit structures. Okay? All right, let's move down here so we have a little bit more room. Okay, the first one is current, and it's defined with capital letter I. Okay, all current is, it's just the flow of electrons. Okay, it's just the flow of electrons. In relationship to circuits, it's the flow of electrons through a circuit. Okay, and it's defined as the charge per second right here. You see that? Charge per second or coulombs per second. So if we have this flow of electrons through a wire, like so, they're moving through this wire. That is the current moving through the wire. That's it. If we have more charge per second, we have an increase in flow or an increase in current. Okay? And this is measured in amps. Okay, or amperes. Okay. Resistance. Okay, resistance is the opposition or resistance to flow. Now, we know that electricity flows through material called what? Electrons, or they're carried, I should say, by electrons. They're those tiny charged particles inside the atoms, the negative guys. So, materials that conduct electricity are the ones that allow electrons to flow freely through them. So, metals, for example. The atoms are locked into this solid kind of crystalline structure, that electron C model we've been talking about. Although most of the electrons inside these atoms are fixed into place, some of them can swim around and move freely through the structure, and they can carry electricity with them. That's why metals are good at conducting. Okay? A metal puts up relatively little resistance to electrons flowing through it. Okay? Plastics are entirely different. Okay? They don't have that same crystalline structure. Their molecules, they're typically these long, repetitive chains. We call these polymers. And they're bonded together in such a way that the electrons inside the atom are fully occupied. Or we say they're fully occupied. In short, I'm saying that there's no really free electrons that can move about in plastics or these insulators to carry an electric current. Okay? This is why plastics are good insulators. They put up high resistance to electrons flowing through them. All right, so what does resistance look like inside a circuit? Or let's draw the wire again here. We have our wire. Electrons moving through it. Now, electrons aren't just going to perfectly move through it. There's always going to be some resistance. There's always going to be some natural resistance, because we know that electrons don't exist. These wires, they're made up of atoms, right? And we have nucleuses, and we have these subatomic particles, and so these electrons battle to flow through it, but as a result, there is some natural resistance. Okay. All right. Now, further speaking, when we get into these circuits, we have these things called resistors. Resistors, and I'll write it right here. Resistors. Okay. Now, what's going on with these resistors? Okay. This is a common misconception, but just listen in and I'm going to bring it home. Okay. This is actually how resistors work. I know some of you have probably Googled it, but let me tell you exactly how they work. Okay, resistors dissipate energy when current passes through them. Okay, what does that mean? Well, that means they convert electrical energy into heat. That means that electrons must give up some energy when they carry current through a resistor. Losing energy means they slow down. So resistors kind of create this speed bump. So electrons move, and they hit this sort of speed bump that slows them down. So it's correct to say that resistors slow down electrons. Now, here's the common misconception. Students think that the number of electrons change when they move through resistors. That's incorrect. The number of electrons remains the same. Current does not involve creating electrons, just putting the electrons or the existing electrons in motion. So resistors do not reduce the number of electrons. Okay, they do not reduce the number of electrons. Got it? Okay, moving on. Voltage. Now, I've posted a lot of videos on voltage. Voltage is all these terms are very abstract, but voltage in particular is very abstract, but we're going to keep it as basic as possible. Okay? Now, voltage and the term potential difference I've used, and we can use them interchangeably. Okay? Potential difference might be better defined as the potential energy difference between 2 points in a circuit. So the amount of difference, which we express in volts, okay, determines how much potential energy exists to move the electrons from one specific point to another. The quantity, volt, identifies how much work potentially can be done through the circuit. So like your household AA battery is around 1.5 volts. Your electrical outlets are 120 volts. So the greater the voltage in a circuit, the greater its ability to push more electrons and do work. So that's why I like defining voltage as the ability to push electrons through. The ability to push electrons through. I really like that definition for you guys. Okay? Now, I'm going to keep bringing up this analogy to a water tank. Okay? Voltage or potential difference or the change in voltage, it can be compared to like water stored in a tank. The larger the tank, the greater the height of the tank, the more electrons can flow through, or the more water can flow through. The electrons in this case, those represent the water. Okay? So, greater the height in tank, the larger the tank, the greater the flow of water, which is the greater the flow of electrons. So I'll keep kind of coming back to this, but let's move on. Actually, let me continue to talk about this water tank. Let me kind of revise this a little bit. So this water tank example. Okay, the voltage is equivalent, let's say, to the water pressure. The current is equivalent to the flow rate, and the resistance is like the pipe size or the hose size. Let's say it's connected to a hose, right? So you have this tank of pressurized water connected to a hose that you're using to, let's say, water the garden. If you increase the pressure in the tank, what's going to happen to the water? Well, more water is going to come out of the hose, right? That is true to an electrical system. Increasing the voltage will result in greater current flow. Okay? Now, let's say you increase the diameter of the hose. Like you increase the diameter of the hose. It was this, and then you made it this. You've increased the diameter. Well, if you increase the diameter of the hose, what's going to happen? Well, more water can come out. This is like decreasing the resistance of an electrical system. Okay? So hopefully that made sense. Now, light bulbs. I'm going to bring this up real quick to finish this off. Now, we can relate this to light bulbs as well. Like, how does a light bulb work? How does an incandescent light bulb work? Well, we can further use this analogy. Okay? The filament of a light bulb is an extremely, extremely thin wire. Okay? This thin wire, because it's so thin, right? It's going to have a high resistance. Well, what happens when there's a very high resistance is that the electrons are going to build up and create a lot of heat, right? As they move and they build up, it creates heat. Well, it creates so much heat that the filament starts to glow and it creates light. All right. So that's kind of analogy to something that's real. All right. A light bulb. Okay. In the next video, I'm going to go over the simulation.